All right, from lots of different observations here, many reactions, lots of experiments. There's a pattern comes out, and then this pattern's reproducible. It's consistent, so we call it a law. And so the equilibrium law looks like this. The equilibrium law says this. This is the equilibrium constant. And it just says that we're going to get a constant number if we take a ratio of the activity of the products raised to their respective powers divided by the activity of the reactants raised to the respective powers. These powers come from the coefficients of the reaction. And it's the equilibrium law here. If we assume ideal conditions, assume ideal conditions, then what we're going to do is we're going to simplify this law here. And that is, if we have all solutions, let's say A aqueous plus BB aqueous, dot, dot, dot. It could be one reactant, two reactants, or more. Goes to one or more products. Dot, dot. Then K, we're going to call KC. This C stands for concentration. And here, we can't use moles unless the number, the stoichiometric coefficients are the same on both sides, and the units cancel. If the stoichiometric coefficients are the same on both sides, then we could use moles, but otherwise we have to use molarity. And so what it's going to do is, if we assume ideal conditions, then Kc, the activity is going to just be the molar concentration. So this will just be the molar concentration of G. There's a little g h, a little h, over A and B. So that'll be Kc. And that's all gases, all solutions. Let's see, all solutions. All right, if we go to 2, which will be all gases. If we have all gases, then A here would be gas plus BB, gas. And same thing, GG, gas plus HH, gas. Dot. If we then we have a choice. We can do Kc, and here we have to determine the concentration, the molar concentration of the gases, which we can do. It's just how many moles of gas per liter. Of course, the concentration is going to be small because gases are not very dense. And then or we could do something called Kp. Kp would just be the partial pressures. And Kp is the partial pressure of gas G over raised to the g power times the partial pressure of h raised to little h dot 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 over a to little a b. Kp is what we call KEQ. KEQ, when we get into the, this is just part of the scientific method here. Usually when we do the scientific method, we take observations, lots, and we get a pattern, we get a law. We can stop here and use the law, but normally what we want to know is we want to know a little more, fundamentally. Like, for example, a question would come up, why do you square it? Why do you square that? Why isn't it multiplied by 2? Is there a reason why we square it? And so we want a more fundamental description of what's going on. And so from here, what we try to do is we don't leave it at this, although we could leave it at this because, in fact, we're going to leave it at this for these chapters 16, 17, 18, because all we need is the law, and we can use the law to predict things. But eventually what I'd like to do is do what? Come up with some kind of eventually I want to come up with some kind of theory, but before coming up with a theory, you don't automatically come up with a theory. So this is to use the proper definition of theory, we can't, a lot of people think, okay, they're going to theorize about, who the murderer was, or they're going to theorize about what had happened, or they're going to theorize about what caused the accident, Actually, those are not, we shouldn't use the word theory for those. Theory should already be accepted. So if you have a theory about the murderer, that means it already has widespread acceptance and people already understand, okay, that's the theory, and there's nothing more to say about it, unless the theory is wrong, of course. So, we call it a hypothesis. A hypothesis is your guess, or you hypothesize. You want to hypothesize who the murderer was, or you want to hypothesize how the exact accident occurred. But once you get widespread agreement on your hypothesis, then that's the theory of what happens. The theory is a fundamental description of what had happened. So this, for example, I've been looking at some of the videos. The plane in Canada, landing, and so there are a lot of hypotheses, about what had happened or what had caused that, plane to flip over and all that stuff, And then once it's pretty well sorted out, then we have our theory. And our theory is the fundamental description of what had happened during that accident, that caused the plane to crash like that. And so, but oftentimes these two things are confused. People think the theory is your guess. No, theory is not a guess in science. Theory is what we're ultimately after, because if we have a good understanding of theory, then we can make predictions. Obviously they want a good understanding of the theory. They don't know, they have to put all the pieces together, but once you have the theory, then what theories, there are two things theories have to do. Do you know what the two things the theories must do? Yeah. One thing is, well, let's talk. There has to be a fundamental description. And so we can see, okay, this is why the plane flipped over. It's a fundamental description of what had happened. And then a theory needs to be able to predict, well, if you do this and that, you're going to have the same type of thing happen. And so it's got to be able to make predictions. It's got to be able to make predictions of new, unforeseen, events. So if you have a good theory, it's not okay if you have the exact same scenario, but if you have a close scenario, what will happen? So theory is very powerful because we want to be able to make predictions. So, there are theoretical physicists. Theoretical physicists, they just guess about things, or they're trying to come up with something ultimately, and the ultimate thing is the theory, And theoretical chemists as well. But we don't need a fundamental understanding, to use a law. If we have a pattern that's reproducible, then we can use that pattern. So KEQ, this is coming from the activities, based on activities. So the activity of a gas is not its concentration. The activity of a gas is its pressure. This, okay, so the question comes up, what is the relationship between concentration and pressure? And so what I'm going to say here is Kc and Kp relationship. Interestingly, Kc and Kp are the same thing if delta N of gas for the reaction is 0. Otherwise, Kc and Kp numerically are different if delta N of gas is non-zero. And that just comes from relationship pressure. If we go back to ideal gas law, P equals nRT over V, we see that we'll get N over V times RT. N over V is moles per liter, and so that's the molarity times RT. This is back from Chem 1A, Chem 4. So pressure and molarity are related here by the factor RT. And so if we look at the easiest equation to derive is this. If they're not equal, how are they equal? So Kp is equal to Kc, or actually, let's not do it. Let me do it that way. Let me erase this, sorry. So it's just, the pressure of the gas, of the products or the reactants. And then the pressure of the gas is equal to the molarity of the gas. The molarity of the gas, we give this symbol, square brackets G, times RT. And then we're going to raise that pressure to the G. The molarity of H times RT raised to the H power. Raised to the B power. So we're just going to factor out the RT's terms here. So this is going to equal the concentration, and I'm going to distribute the G here. So this is going to be just do a little bit of simplification here. And so when I multiply, I add them up. So this is G plus H plus dot dot dot. RT term. A plus B dot dot dot. And so you recognize the first part of this. If you look at the first part, do you recognize this? This is just what? That's just Kc. And then we're going to use the properties of exponents. We're just going to combine these. And so what we'll do is we'll just go G plus H plus dot 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 minus A plus B plus dot dot dot. And when we look at this, this is the number of moles of product gas minus the number of moles of reactant gas. The number of moles of product gas minus the number of moles of reactant gas we call delta N of gas. And so if we, let's say we go from 3 moles to 4 moles, delta N of gas is plus 1. If we go from 4 moles to 3 moles, delta N of gas is minus 1. And so it's just how many moles of gas did we go. If we go from 4 moles to 4 moles, then delta N of gas is 0. When delta N of gas is 0, then the RT term drops out. And if the RT term drops out, then Kp and Kc are equal. Okay. So we use this to interchange between Kp and Kc. 3, we have a mix of states. If we have a mix of states, well, let me go back to here. I'm going to call this, I'm going to label some of these up here. So I'm going to label this KEQ because this is going to be based on the activities, and then this is equal to KEQ here, KEQ. So KEQ equals Kc when we're dealing with just solutions. KEQ is equal to Kp when we're dealing with gases, but what happens if we have a mix of states? If we have a mix of states, then we just remember this. The activity of solutions is about equal to the concentration. The activity of a gas is about equal to the partial pressure of the gas. And the activity of solids is just 1. And the activity of liquids, pure liquids, is just 1. Now, activities have no units. They're dimensionless. Therefore, when we make these assumptions, we ignore the units. Because really we're supposed to be doing activities. And so we go back up here, we ignore the units. We should be using activities. Actually, the units will drop out. When we put in what they call the activity coefficient in here, the units drop out. But we're making our life easier by doing it like this, assuming ideal behavior and not having to use activity coefficients. You have a chance to review the activities page too. It's best, again, it's best not to review it the night before the test. Reviewing things like the night before the test causes undue stress, I think. All right. So so far, what have we done? So far, we've seen how if we take a whole bunch of experiments of the same reaction, we can see the pattern and we can get K. So K is extremely useful. K, okay, there are two things, determination and application. So we saw an application of K. What did we apply K to? We applied K to predicting stoichiometry. Stoichiometry is just quantity relationships, right? Determination. How did we determine K? By experiment. We had 3 experiments that we averaged, right? The average K came out to 1.48 is the average K value. Right, the more experiments we do, the more we can minimize what type of error. Yeah, the more experiments we do, the more we can minimize what type of error. Not numerical. Random error. That's good. That should have been like that, you know. It should have been, that's why you might want to, because do you know, my memory is bad, but but I try to make the best use out of it. And so I read some memory books when I was a student. And study books, you know, how to study, that kind of thing. I read a lot of those. But you should, if you hear, like, if we talk about random error yesterday, what was it, yesterday? The day before yesterday, you know? What you want to do is you want to refresh it, because the longer you wait to refresh that memory, the more likely it's going to disappear, you know? And so, you know, at the bare minimum, it would be good to, after class, just review your notes. When I ask if there are any questions, I know people aren't reviewing their notes, you know, because you review your notes, questions may come up, you know, sometimes, but nobody ever has any questions usually. Which surprises me, because I get a lot of complaints, you know, oh, you know, it's not clear, I don't understand this, you know. Well, what you want to do is you want to just read through your notes and just make sure. And then at least it registers once, and the more frequently you do that, the more you'll remember it. But also it'll clue you into what you need to review or to clear up before the test comes. Now, experiment is a lot of work. Are there other ways of determining K without doing a lot of work? And it turns out, yeah, there are other ways of determining K. Other methods that don't rely on experiments, on doing an experiment. And so we're going to look at relationships, K relationships. If you reverse the reaction, such that the products are now the reactants, GG plus HH plus dot, 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 dot. Then K of the reverse reaction is equal to 1 over K of the forward reaction. But, you know, these are two-way reactions. Since these are two-way reactions, we rarely do this. Because we'll just say, okay, the reaction goes in reverse. You know, no, experiment two, I didn't rewrite it to make the products now the reactants. I just said it's going to go backwards, right? So typically we don't do this unless we're doing these other things. Now the other things are going to be like Hess's law. And so the sum of the steps gives us the net reaction. And K for the net reaction is going to equal K1, which is step 1, times K2 times K3. So this is like Hess's law. This is Hess's law, but in Hess's law we add up the delta H's or delta U's. But for equilibrium constants we multiply. Like Hess's law, but multiply. But multiply, not add. If we multiply, let's say we have our reaction and we multiply it by N. So this is N times AA plus BB plus etc. If we multiply by this N, then K for this is equal to K of the original raised to the nth power. So if we double everything, then we have to square the original K. So people have done lots of experimental work. There have been a lot of work, and this lot of work is compiled in tables. In tables here. So we're just going to take advantage of other people doing the work for us, and if something new comes up, then we'll try to figure it out based on these relationships here. Yeah. Just need to go to the textbook. These K values are compiled in small tables in the chapter or in larger tables in Appendix D. So let's take a look at some K values from Appendix D here. The data tables. So table D1, ground state electron configurations. Table D2 is just thermodynamic data here. D3 is the equilibrium constants. So here, now we have K values here. These K values are Kc values here. And these are for aqueous solutions, but we call them Kas. Kas because they're for a specific type of reaction. All these Kas are for acid hydrolysis, acid plus water reaction, where water is the base. So the base is going to be the same thing for all of these. So what we're comparing is, how reactive are these acids towards water our base. And so we can compare the acid. And this is going to give us an idea of acid strength. So these are called Ka, or acid dissociation, or acid ionization, or acid hydrolysis. Equilibrium constants here. So that's in D3. This is chapter 16, which we're going to start, or 17, which we're going to start today. Here's another K. This K is called the solubility product. And it's also Kc value, so this is called Ksp for solubility product. Solubility product is looking at the equilibrium between the solid and the aqueous ions. There's going to be a dynamic equilibrium. We're going to have dissolution of the solid and crystallization or precipitation of the ions. And we come up with saturated solutions. So this tells us how much of the solid dissolves. These are all solids here. How much of the solid dissolves in water. It's chapter 18. These are complex ion formation constants. And, this tells us about the formation of these. So we take a silver ion and two cyano-ligands and then have them react. And so the reaction is the silver plus the cyanos react. And how favorable is that reaction? When you look at it, look at that K value is 10 to the 18. It's a big number, isn't it? That tells us it's very favorable. Cyanide loves silver. Loves silver. In fact, if you look at cyanide, compare that to EDTA. EDTA is not even close. I mean, 10 to the 7. Ethylene diamines. We got 2 ethylene diamines. So what's the coordination number of silver here? 4. Yeah. But typically the coordination numbers, well, the coordination number here is 2. What's the coordination number here? 6, 4, 2. So, just do it. We have 4. Thiosulfate. Is that bidentate or bidentate, monodentate? What is that? Thiosulfate. It's monodentate. Two oxygens are too close together. Sulfur is too close together. But anyway, we have K values for this. Now, how do you predict, so for example, how do you predict some of these things? Like when I look at this, what reacts with what? And so what we're going to do is we're just going to look at tables like this. We're not even at the pattern phase. We're just at the observation phase. At the observation phase, we just need factual data. If you want to predict what's going to happen, you're going to have to mix it together and do an experiment to see what happens, kind of thing. Unless somebody's already done it. If somebody's already done it, that's good. Because what we need is a consistent pattern. Is there a consistent pattern? There probably is, but it's just too complicated and it's too much to memorize.
Wait, how do you know that S2O3 is?
Because I know the structure of S2O3. Can you visualize the structure of S2O3? Can you visualize the structure of sulfate? If you can visualize the structure of sulfate, then the structure of thiosulfate is easy because do you know what thio means? Here. Thio means replace an oxygen with the sulfur. Sulfur and oxygen are the same family. So I can easily determine that thiosulfate's monodentate just by picturing sulfate or thiosulfate in my mind. And then seeing. So we'll just do a side topic here. Is sulfate a monodentate or a bidentate ligand? I'm going to do this structure, the expanded octet structure of sulfate. Because typically this is the one that's normally shown. Out of these 2 oxygens, or 4 oxygens, which one should be the most basic? Obviously, we know if you do the expanded octet structure like this, all the oxygens are How many resonance forms can you draw for sulfate? The way well, I don't want to spend too much time talking about 1A stuff. The way I determine resonance forms really quick is I'll fix this double bond here, and that gives me how many positions for this other double bond. 3, right? And then I'll move this double bond. If I move it to this double bond, in the tetrahedron, all sites are equivalent. You know, there's no top and no bottom. It's like a ball. It's spherically symmetrically same. And so 4, maybe. If I flatten it out, it's easier to see. You know. So oftentimes people will flatten it out. Okay, so we have top left 1, top down 2, top right 3. Okay. And then left, you know, and then we just count them. How many different, maybe 6, I don't know. But we'd figure them all out. But what we'll do is, in this case, what we're going to do is we're going to just do valence bond. In this case, the other way of writing sulfate is better. What's the other way of writing sulfate? You know, there's some controversy about writing it this way. Can somebody tell me what the controversy was regarding writing it this way? Although everybody writes it this way, what was the controversy? And so what was the alternative? Actually, just tell me what the alternative way of writing this is.
Just like a regular octet?
I'm sorry, Tristan?
You mean with like just a regular octet?
Yeah, with a regular octet, right. Oh, my word has died. I think I exceeded it. Must be. The other way is just leave it as an octet. Formal charges are kind of high. The reason we expanded the octet there was to minimize the formal charge on sulfur and lower the number of oxygens that have a formal charge, but now it's going to be +2 on sulfur, whereas in the other structure it was just 0. So the controversy was surrounding the participation of d orbitals in bonding. In Petrucci and Chem 1A, there's a statement about recent quantum mechanical calculations showing like no d orbital participation in bonding. And so this expanded octet idea was, so this might be a better representation of the structure. Better representation, we have this higher formal charges, which isn't great. I mean, a +2 formal charge on sulfur isn't great, but there's some ionic. So this is a mixture of covalent and ionic bonding here. Ionic bonding is just the electrostatic attractions here. You can go back and look at that. I don't know how crucial it is. But actually, the two oxygens are the same. And if you did the quantum mechanical calculation, all the bonds are exactly the same, and all the oxygens have the same charge. Although they might not all have -1 charge, it's probably lower than -1. But anyway, getting back to this, the oxygens with a negative formal charge are going to be the ones. And so if I use the original structure, which I'll do because that's what probably people are more familiar with, we would try to go ahead and bond it. And so I would take the oxygens with a negative formal charge first and attack the central metal here. This is tetrahedral, so, you know, all these positions are the same. And so we put a metal plus X here, and then attack the metal here. Monodentate or bidentate. Monodentate. Rebecca, why is that monodentate? How did you come up with that? You just memorized it from the chart? Okay. Yeah, you could do that. You could memorize it from the chart, but sometimes something's not going to be on the chart. If it's not on the chart, then how would you recognize it as being a monodentate? I better save this before. What's the problem with going bidentate here? Is it begun? Yes. Is it because it's going to be a square? Yes. And what's wrong with being a square? Yeah, angles are too small, 90-degree angles. So the answer would have been the bond angles would be too strained if this were to happen. It's a four-membered ring. You guys remember four-membered rings and smaller? And five-membered rings and bigger? You should memorize that, too. That would be more powerful than just memorizing the monodentate ligands on the chart. Now, what about thiosulfate? Thio just means sulfur. So thio means replace oxygen with sulfur. That's fine because oxygen and sulfur are in the same family. So I'm going to replace one of these oxygens with the sulfur. Any difference here? No. It's going to be monodentate as well. You see that? It's got to be monodentate. And so thiosulfate's a monodentate ligand. So we have data tables full of K values. We're going to use those K values. Other people did the experimental work. We want to try to minimize the amount of experimental work that we have to do because experimental work is extremely time consuming. So what we're going to do is we're going to do applications of K. Application of the K, we just, solve for X basically. And so we're going to have the initial A, initial B, initial G, initial H. And then there's going to be a change. The change is going to be either minus AX minus BX plus GX plus HX, or the change is going to be plus AX plus BX minus GX minus HX. This is if the ratio is too small. This is a ratio too big, or the change could be 0. 0, 0, 0. Ratio here is too small. If the ratio is too small, we need more product. Ratio here is too big. We need to get rid of product and make more reactant. Here, the ratio is just right at equilibrium already. You know, and the initial, it might already be at equilibrium. We might not have to do anything, and then we'll have our equilibrium states. You know, here, the equilibrium state of A, etc. So we need to know, is the ratio too big or too small, because that's going to tell us the direction of the change. And so what we do is we determine the direction of change by calculating something called Q. Q is the initial G, you know, raised to the G, initial H raised to the H, or the initial A raised to the A, initial B raised to the B. Initial here refers to the initial whatever concentration. Concentration, pressure. You know. So it depends. If it's all aqueous solutions, you know, what we do is we have something called QEQ. We have QC and QP.
How is Q related to
K
K?
is the equilibrium. G to the G, the equilibrium H, H. It's the equilibrium values, whereas Q is the initial. So we just take the ratio of the initial. K values we look up in the table, look up or determine. You know, if it's not in the table, then we're going to have to determine it one way or the other. And so to determine the direction of change, we compare Q versus K. If Q is too big, then we have too much product, and we got to go backwards. If Q is too small, then we don't have enough product. We got to go forward. Change. If Q is just right, then there's going to be no change. Zero change. And so what this means is going to be plus plus, minus, minus. Over here, this is going to be minus, minus, plus, plus, you know. If you screw up the direction of change, it doesn't matter. You'll still get the right answer. Like, for example, if you keep track of the signs, you know, it's supposed to be minus, but your x comes out negative. If your x comes out negative, then maybe you screwed up the direction of change, you know, something like that. But it could still work because a minus times a minus is a plus. So, for example, if you're starting off with 0 and you get a minus x, well, you might have screwed up the direction of change. So sometimes we do this. We do this when it's not clear. It's clear if there's a 0. If there's a 0, then it's easy, you know, because you can calculate in your head. So, for example, if we have 0 initial product, then Q is 0. Or if we have any of these reactants, if any of these reactants are 0, then we have a Q of infinity. And so whenever there's a 0 there, then calculating Q is very simple. You can do it in your head. Or you can just look at it and see what the direction is. But when we have a whole bunch of different things in there, then it's hard to determine which direction it should go. Should we lose reactants and gain product, or should we gain reactant and lose product? So that's it. And so this is the bulk of the calculations. You know, this is the most important stuff. Here is the stoichiometry. Okay. Now, there is another application of this, which is a more narrow application. It's Le Chatelier's principle. And conceptually, this is very useful to know. Le Chatelier's principle just says a system at equilibrium can be upset. And so let's say everything is already at equilibrium. And you screw it up. So everything's at equilibrium. So what we have, let's just do concentrations here. It could be gases, whatever. This is at equilibrium. B is at equilibrium. G is at equilibrium. H is at equilibrium. So everything's perfect now, and then all of a sudden you decide to throw in some more A. And so now we have a balance, and you can upset that balance. The balance can be upset by increasing the concentration of any of these. And so, and then we have gases, you know. Gases, all gases, and then mixed states. What we do is we perturb the equilibrium. We screw up the equilibrium by messing up the ratio. We perturb the equilibrium and then determine how equilibrium will be reestablished. So there are factors that we consider. One is changing concentrations. So if we increase the reactant concentration, then we have too much reactant. And so we end up shifting the equilibrium to the right, and then it'll reestablish. So let's say we have a scenario here. We put some water in here. Let's say we have a weird tub that's filled like this. And the left side we're going to call the reactants, the right side we're going to call the product, and this is just H2O liquid in this tub. So what I'm going to do is, this is at equilibrium right now, do you see? The water levels are equal. But what I'm going to do is I'm going to screw it up by dumping more water on the reactant side. I forgot to talk about one thing, which I'll talk about right now. Do you see how I drew these unequal sides? So the water can go back and forth equally. In fact, this is going to be under dynamic equilibrium. It's at equilibrium because the two levels are equal, but it's dynamic because the water can travel back and forth. It's just that the number of water molecules traveling to the right will exactly equal the number of water molecules traveling to the left, otherwise the two levels won't be equivalent. So we have a state of dynamic equilibrium. But when I look at this, which side is favored? Is the product side favored or the reactant side favored? Product side's favored because it's bigger. I have more product than reactant. And so when we see this, if K is greater than 1, then what's favored? If K is greater than 1, then we expect the when we have K greater than 1, then product is favored. If we have K less than 1, then reactant favored. And a K equal to 1, then both. And so K equal to 1, how would I represent that? How I'd represent a K equal to 1 is I'd draw two equal sized wells on both sides, or two equal sized volumes on both sides. That would be K equal to 1. So this would be like a K greater than 1 type thing. Product of favored. So if I dump in more water on the reactant side, what's going to happen? Well, it's no longer going to be at equilibrium because one side's going to be bigger now. And so let's dump in more water here. Is this at equilibrium now? No, what's going to happen is there's nothing preventing this water from flowing to the right, and what's going to happen is I'm going to have a shift, we call it. This is going to go shift right, and then I need to reestablish equilibrium. And so I'm going to reestablish equilibrium, but when I look at the new equilibrium, is it going to be exactly the same as the old equilibrium? No, because I'm going to have more water on both sides. And so I'll have new equilibrium here. So I have a shift right, but both sides grew. So what we do is we do this. We do a change. It depends on where you measure the change from. And so we're going to look at that. The change from the original to the new, what happened? We increased the reactant here, right? However, the change from the perturbed to the new, what happened here? We decreased the amount of reactant. And the change from the initial here and the perturbed will be the same. That's going to result in an increase in product. Equal. So sometimes what we have to do is we have to predict, okay, there's going to be a shift to the right, but sometimes we have to determine, what happened to the reactant. And it depends on what your reference point is. If your reference point was the pre-perturbed equilibrium state, it's different than the post-perturbed state here. And so you have to be careful. What are they asking? Because sometimes they'll ask you what happens to the reactant. Does the reactant increase or decrease? Well, it depends on where you're talking from. If you're talking from the initial, the reactant increases. If you're talking post-perturbed, then it decreased. And so just be aware of that. So if we increase the concentration of the products, then we're dumping water into the product side. Which way is it going to shift? It's going to shift to the left. Okay, if we decrease the concentration of the reactants, which way does it shift? Shifts to the left. We need more reactant. If we decrease the concentration of the product, what's going to happen? It's going to shift to the right. All right, the pressures do the same thing. Pressure and concentration are related. So if we're dealing with gases, we have the same type of scenario. And so if we're looking at the partial pressure of the reactant gases, increasing that will shift right. Decreasing this will shift left, and then the same thing with the product. Increasing the product shifts left, decreasing the product shifts right. Okay. Volume is a little bit tricky. Increasing the volume let me do one more thing about pressure. Sometimes they'll throw in a trick thing. This is a trick question. Increasing or decreasing the total pressure may or may not have any impact, because it depends on how you increase the pressure. And so no change if pressure was increased by adding inert gas. P total was increased by adding an inert gas. Inert means it doesn't react in that reaction. But if the total pressure was changed by changing the volume, then it will have an impact. And so if we increase the volume, which decreases the total pressure of a gas, or gases, then this favors the side with more moles of gas. More gas. N of gas. Moles of gas. If we decrease the volume, we squeeze it down, then it's going to favor the side with fewer moles of gas. And so it shifts to whatever direction that is. None of these change the K value. The equilibrium constant. They just upset the Q ratio. You know, it's a perturbation. So none of these change the equilibrium constant, K. Temperature does change K. And so we're just going to do this qualitatively for now. Increasing temperature favors the endothermic reaction. And whichever direction is endothermic, so it could favor the forward or the reverse. Decreasing temperature favors the exothermic direction. Both of these change the value of K. So we always specify, therefore, we must specify the temperature for the K values. And the example I'll just give here is a K at 298 Kelvin is not going to be the same as a K at 1000 Kelvin. If the temperature is not specified, what temperature do you think they're talking about? 1563 Kelvin? If the temperature is not specified, what temperature do you think that K value is for? Room temperature. Yeah. And so if they didn't specify the temperatures, you're just going to make a pretty safe assumption that they're talking about room temperature. Do you see all the K values in this chart over here? Yeah, the all K values for these reactions here. When we look at the K values, you can tell by the magnitude of what's favored. So take a look at the K value up there. You know, there's not even a number on it. Let's see. Show you the chart here. Actually, let's see. Probably I'll go to our book. See, it's easier to see than that wall chart. This time I'm not going to go to Appendix D, although that table is in Appendix D. Let me see if they have it. I want it ranked. That table is here, but I think it's in alphabetical. Yeah, it's in alphabetical according to the acid. I don't want it alphabetical. I want it based on strength. So they start off with A for acetic acid. And then they end up with T for trichloroacetic acid. But in chapter 16, they have this, or chapter 17. Chapter 17, they have this based on strength, I hope. Actually, no, they don't have it based on strength. So we'll just look at this table over here. Normally we want a number here, but they don't give us a number. What do they call the K value for this? Just read it. Read it. Very large. Is there a button on your calculator called very large? So you hit the very large key on the calculator and then you can do your K calculation. Yes? No, unfortunately there's no button on your calculator called very large. So if the K is very large, does that favor product or reactant? It favors product. And if they say very large, then what number should I use there? Should you use like 100? Is that very large? 1,000? A million? A billion? Trillion? I don't know. So what we do here is we assume it's so large that it's all product. You know, to really properly be all product, it's got to be infinite, infinitely large, but it's not. But we're just going to assume it's close enough. And so this isn't infinite. There's actual numbers for this, but what we do is we don't even bother, because what we say is strong acids do what? Strong acids completely dissociate from the product. These are the products here. So we have 100%. So we aren't even going to bother doing calculations. This is like Chem 1A. It just goes to completion. Does that make sense? However, when we start getting like 1, well, 1 is like, we should have a good mix of product and reactant. And the same thing with these. These are close to 1. I mean, that's 1/100 or something like that, or 1/600. And so, but then we go on and on and on, and then eventually we hit this point where K is very small, which essentially is like no product, no reaction. I mean, ideally it's 0. 0, you have no product, right? But this is very small. There's not much there. But anything in between very large and very small, we're going to do a calculation for that here. And we're going to do an ice table. We're going to figure out, even if it's a little bit. And so the small one, this is heavily reactant favored. And so these are weak acids. Weak acids only partially hydrolyzed. But we want to know how much. And figure that out. And so the magnitude of the K value is going to tell us that. And so when we move on here, I'm going to, there's some chapter 16 practice problems, and I might give you a harder chapter 16 problem to do, but we're going to move on to chapter 17 here. And let me just say in the last minute, we have what, 1 minute left? 2 minutes? Is that right? We're out of here at what time? 55? 11? Oh, we have 6 minutes. It's even better. All right. So we're going to be looking at these ionization or hydrolysis reactions. So we're going to devote the entire 2 chapters, actually. 2 chapters of looking at acid ionization or acid hydrolysis. This is an acid ionization chart, and we can look at hydrolysis or ionization reactions here. In chapter 17. So let me go back here. We're going to do experiment with Le Chatelier's principle on Monday. So I was thinking we'll have the chapter 24 quiz on Monday, and then, or at the end. We'll first do the reactions. We're just going to perturb an equilibrium. So how we're going to perturb the equilibrium, we'll just add some drops. Did you guys look at Canvas recently? I put the experiment should be there, so take a look. We're not going to do the entire experiment, so just skim through the experiment. But we're going to perturb it and visually see what happens to particular reactions. Chapter 17 is Acids, Bases, Part 1. So the first thing is we need the acid hydrolysis reaction and the base hydrolysis reaction. we're always going to write it like this. So if we have an acid, let's say HA, HA is our acid, and A is just some generic anion. This is acid ionization, which is fine, but what we're going to do is the proton is unstable in water, and it's going to attack water immediately to form hydronium. In Chem 1A, I had everybody write it as a proton. In Chem 1B, we're going to write it as hydronium, like this. Oops. All right, so we can come up with Ka. Ka is our acid hydrolysis. Ka is the products, and so we have hydronium as a product. And that's going to be raised to the first power. And then we have our A minus raised to the first power, divided by our HA. What do we do with water? Water has an activity of 1, and so we usually don't even bother writing 1 in there, unless that's the only thing there. And so this is Ka. If we have a diprotic acid or a triprotic acid, then that changes things. This is a mono. This is go to a diprotic acid, which would be H2A. A, again, is a generic cation. Now, both protons don't break off at the same time. They break off one at a time. And in fact, once you break one off, the second one is a lot harder to break off. And so the first one's always the easiest. That'll be H3O plus. And so if you have a diprotic acid, what you have to do is you have to deprotonate the first one off all of them before you can deprotonate the second one usually. And so we do that, and we call this Ka1. Actually, I'm going to call this Ka1 for H2A, which is going to be the hydronium times A minus over the H2A. Now, the math in this chapter is easier because, do you know, we're only going to get second order. That's going to be the highest. So quadratic will be the highest. In the previous chapter, the math gets horrendous because we could have, well, it could be easy. We get lucky. It's quadratic. Or even easier. Sometimes the square terms cancel on the top and bottom. And we have something even easier than quadratic. It's just simple algebra. But it can get very difficult. 6th order, 7th order polynomials, which are hard to deal with. Now, this, we only lost one of the hydrogens. So this is actually HA minus, sorry. And to lose the second one's a lot more difficult. And so water is going to struggle plucking the second hydrogen off. And so we have two K values here. We have Ka1, and then we have Ka2 for H2A. Ka2 for H2A is equal to Ka for HA minus, which is equal to the hydronium concentration times the A2 minus concentration divided by the HA minus concentration. And so we have a Ka1 value and a Ka2 value for diprotic acids. For triprotic acids, we'll have a Ka1, Ka2, and a Ka3. And so for a triprotic, we'll have H3A plus H2O liquid. This is going to give us hydronium plus H2A minus. This is Ka1, and then H2A minus plus H2O liquid is going to give us hydronium plus HA2 minus. This is Ka2, and then finally HA2 minus plus H2O liquid. It gives us hydronium plus A3 minus. This is Ka3. This is Ka1 for H3A. This is Ka2 for H3A, which is equal to Ka for H2A minus. This is Ka3 for H3A, which is equal to Ka for HA2 minus. Okay, and that's it. So stop here, sorry. All right, so this is chapter 17, is just applications of this equilibrium stuff.